Hello, I am Zach Scott, a student at the University of Nebraska-Lincoln's Department of Computer Science and Engineering. Today I will be presenting my final project for CSCE 440 over the reconstruction of damaged audio files using interpolation. A quick discussion of theory. Digital signal processing is a field which uses computers to manipulate signals such as audio files. Recording audio using continuous values is not feasible due to memory and time constraints. Instead, a sampling frequency is selected, then at corresponding time intervals, samples are taken from the original signal. These samples can then be used to play back audio. This project seeks to explore how well interpolation can reconstruct the original signal if some of these samples have been lost. Any audio file can be used for the purposes of this project, though I wanted to find one with few, if any, consecutive zero samples, as a zero sample for the purposes of this project are considered damaged. I have selected the Cooper Institute's FitnessGram Pacer Test audio track. To keep time to run reasonable, I used the first 100,000 samples of the audio file, which was sampled at 22,050 Hertz. 3 levels of damage were done to the file using a MATLAB script. Each sample had a 10%, 50%, and 90% chance of being zeroed. Comparing the undamaged audio file to the attempted reconstructions of the 3 levels of damage will allow measuring the fidelity of the reconstructions and demonstrate the limitations of interpolation. Here are plots of the full 100,000 samples showing the original signal and the 3 damaged signals in green, overlaid on the original signal in black. These plots may not display the level of damage adequately, so we'll look at the first 100 samples of these plots. With these plots, the significant differences between the original signal and the 3 levels of damage become much more perceivable. In order to attempt to reconstruct the original signal from the damaged signals, 2 interpolation methods were used. The first is linear interpolation, where I searched for zero samples, then calculated the slope between the previous sample and the next non-zero sample to create a slope-intercept form equation used to replace the zeros between these 2 points. The second method is cubic spline interpolation, for which I used MATLAB's built-in cubic spline interpolation function, spline. Here are the full plots of the 6 reconstruction attempts. The reconstruction attempt is in green and is overlaid on the original audio in black. Both methods produced reconstructions that were very similar to the original audio at the 10% damage level, and the reconstructions for the 50% damage signal is still fairly similar to the original signal. However, attempts to reconstruct the original signal from the 90% damage signal proved to be highly inaccurate, with the cubic spline interpolation generating many significant overestimations. Looking at the first 100 samples of the 6 reconstruction attempts gives us a better idea of how different the 2 methods behave at the 3 levels of damage. We can treat the reconstructions from the 10% damage signal as being near perfect reconstructions of the original signal for their given method due to the numerical error I will go over on the next slide. One item of note is the inconsistency of shape in the reconstructions from the 10% damaged file, the increased consistency of shape in the reconstructions from the 50% damaged signal, and the high consistency of shape in the reconstructions from the 90% damaged signal. Judging from the reconstructions of the 10% damaged signal, in the case of the original signal used in this project, inconsistency in the shape of the reconstruction means a more accurate reconstruction. These plots display a clear limitation of interpolation. Interpolation creates a consistent curve between samples. When interpolation is used to reconstruct inconsistently shaped data, the more data it has to work with, the better this inconsistency is represented. However, when there are fewer points to base an interpolation on, the inconsistency of the data is lost due to the interpolation's attempts to reconstruct it with a consistent curve. As we will see in the next 2 slides, this can have serious ramifications. Here are the average percent errors for the damaged signals and their reconstructions. Note that the error of the damaged signals is approximately equal to the probability of zeroing samples at their corresponding level of damage. I have also included adjusted average percent errors. These were calculated by ignoring reconstructed samples that have a magnitude that is at least 10 times greater than the magnitude of the corresponding original sample. Reasonably, reconstructions from a less damaged signal have less error. We can also note that cubic spline interpolations, at least for less damaged signals, are more accurate than linear interpolations, especially when over-approximations are not considered. We can also observe that more over-approximations are produced by cubic spline interpolation than linear interpolation, and that they differ much more significantly from the original signal than those from linear interpolation. Numerical error can only give us some idea of how accurate the reconstruction is, but listening to the resulting audio is a better illustration of the capacity of interpolation to reconstruct damaged audio. First, the original signal.
The fitness gram pacer test is a multi-stage aerobic capacity test.
Then the 10% damaged signal.
The fitness gram pacer test is a multi-stage aerobic capacity test.
Its linear interpolation reconstruction.
The fitness gram pacer test is a multi-stage aerobic capacity test.
And its cubic spline interpolation reconstruction.
The fitness gram pacer test is a multi-stage aerobic capacity test.
Next, the 50% damaged signal.
The fitness gram pacer test is a multi-stage aerobic capacity test.
Its linear interpolation reconstruction.
The fitness gram pacer test is a multi-stage aerobic capacity test.
And its cubic spline interpolation reconstruction.
The fitness gram pacer test is a multi-stage aerobic capacity test.
Finally, the 90% damaged signal. Its linear interpolation reconstruction.
The fitness gram pacer test is a multi-stage aerobic capacity test.
And its cubic spline interpolation reconstruction.
The fitness gram pacer test is a multi-stage aerobic capacity test.
The reconstructions from the 10% damaged signal are nearly indistinguishable from the original signal, and the reconstructions from the 50% damaged signal are somewhat noisy, but their content is still clearly that of the original signal. Reconstructions from the 90% damaged signal are incredibly noisy, but are far better representations of the content of the original signal than the 90% damaged signal is before reconstruction attempts. In conclusion, interpolation cannot recover lost samples, only attempt to reconstruct the overall signal using the remaining samples. Cubic spline interpolation is more accurate than linear interpolation, but results in more outlying samples which lie farther from the original signal than those produced by linear interpolation. Using interpolation to reconstruct a mildly damaged signal can produce a signal that is nearly indiscernible from the original signal. The noise in moderately damaged signals can be significantly reduced, and greatly damaged signals can be somewhat salvaged, but at very poor quality. Further developments in this project could compare cubic spline interpolations of the full signal against cubic spline interpolations of the signal in uniform chunks, say 10,000 sample chunks. The inconsistency of a signal shape may be better maintained when the reconstruction is based on samples in chunks instead of samples in the entire signal. Thank you for your time and attention. If there is any time remaining, I'd be happy to take questions any of you may have.